This work is something that has been ongoing for a while. The aim, of course, is to look at QCD, but we have not succeeded. So what I'll be talking about is essentially looking at a theory of QED of interacting particles which are both scalars and fermions. And I will tell you what is this infrared problem, and that is the first part. And then I will tell you what is the thermal field theory. So I'm interested in the field theories which are not at zero temperature, but are at some non-zero temperature, and that has implications for example, when you have collisions at RIC or the upcoming EIC of very heavy ions, and you produce quark gluon plasma, and they are always hot plasma. So that is one context where these are interesting. That is why the interest in QCD, but they're also of interest in the early universe, of course, which we know was hot. So I will tell you a little bit about infrared divergences, and then I will start out by telling you a little bit about what cross sections are. So hopefully, we will go in that order. So this is, I think, usually I skip this, but I will actually tell you what are the preliminaries and where you can start to kind of get lost, so that, get lost in the details. So I will have some preliminaries. I will review what scattering theory is, at least if there are any MSc students. I will do this in non-relativistic quantum mechanics. And then I will talk about quantum statistical mechanics, because that forms a natural framework where you introduce temperature, because you know that always your statistical mechanics systems are at some temperature with certain distributions. So I will talk about that. And then I will try to merge them together and tell you what a thermal field theory is. And here I will wave my hands, but hopefully still you will be able to understand the formulation that I will set up. And we will then write the Lagrangian that is of interest to us. And I'll explain why it is a QED Lagrangian. And then here starts a little more technical part. I've still kept it like as simple as I could, but I am not satisfied, as I said. So I will give you I will describe to you why the infrared problem is already serious at T equal to 0. And then I will say how it becomes actually even more acute when you turn on the temperature. So I will write both these things, and then I will tell you how we have actually shown in some particular whatever for this particular Lagrangian that of interest, that we have actually shown the infrared finiteness of the cross section to all orders in perturbation theory. And then I will end by just telling what we have got when we compute actually just the first order correction to the leading cross section for a process where chi is a dark matter particle and it annihilates to a pair of fermions. And this is again of interest in the early universe. So this is where I will start. So I have already mentioned these words. Unfortunately, I was supposed to ask Rakesh to interchange with the next speaker, Narendra, because he will be talking about dark matter. So if you don't know what dark matter is, just wait for the next talk. You will learn all about it then. But we are sure that dark matter exists because of certain evidences that we have seen from very many astronomical, astrophysical, and cosmological observations. So we believe that we do see evidence for dark matter in the early universe, but we don't know whether it has particle content. We don't know anything about the nature of dark matter. We have not seen it in the lab. However, I will take a model which represents dark matter interactions with known standard model particles, and I will compute this cross section as I have promised, and I will tell you something about the context in which we calculated these corrections, and then as I said, I will show that we have a proof of all order cancellation of infrared divergence. So this is what I want to actually say in the rest of the talk. So now let us start with this is something you would have read about in quantum mechanics as Fermi golden rule, which tells you how scattering processes occur. So I have H naught time independent Hamiltonian where everything is known. I know exactly how to solve it. Maybe it's some harmonic oscillator or something which has exact solutions. So I know the stationary states. I call them UN, and H naught on U gives you the energy En for the nth state UN, and of course they are orthogonal states. So they are normalized as UN star is delta Mn. So this is completely known Hamiltonian. Now I want to turn on a perturbation, this H interaction, which is the potential actually. And we always believe that the potential is turned on at some time t around 0. And in the distant past, t minus infinity, we have states which are essentially these eigenstates of the time-independent Hamiltonian H naught, because there is no potential at that time. And again, when we make the measurement At the detector, which is at t going to plus infinity, again there is no effect of the potential, and there we still have only the pure states of the H naught Hamiltonian at that time. So our scattering theory, and this is very important when we do the thermal part, is that in the distant past and in the distant future, we have these eigen states and eigenvalues of the unperturbed Hamiltonian H naught. Okay, and this can be a little subtle and non-trivial in the thermal case, which I will not discuss in this talk, but it is something to remember. Okay, so now we turn on this potential, this H interaction, which is V, and let us assume without loss of generality that we started out in some state alpha of this eigenvalue of this H naught. It started out in alpha, and then suddenly it sees this potential, and now it's no longer a stationary solution, but we can assume that this interaction Hamiltonian takes the system at t going to plus infinity to some state beta, which is also an eigenvalue of H naught. So this is the usual context in which scattering theory is set up, and this is the usual Schrodinger equation, I d psi by dt. So in my talk, H cross equals C equals 1. So please put them back wherever required. So they were, I don't remember exactly where all they come. At least here there's an H cross, which I have dropped. So I d psi by dt is H psi, and H is H naught plus this interaction piece. Now, the main way in which you solve the Fermi golden rule is to realize that these phi n form a complete set of states, and therefore you can always expand this unknown psi because you cannot solve it exactly anymore because of the presence of this perturbing potential, and therefore you can always write it as a sum over this basis set phi n with coefficients a n, and I've just substituted for phi n over here from un e to the minus I e n t. This is the time dependence, this is the x dependent part, and these coefficients a n will tell you the probability that the psi is in a particular state e n, right? This is the standard way in which we do this expansion. So before this was nothing. I mean, before this was some motivation.
But what is the? I didn't understand. What was the question that you're trying to answer?
I have to set up two things. I have to set up cross section, and then I have to set up Lagrangian, and I have to set up Feynman rules for finite temperature field theory. So I will set up the cross section formula. I will set up statistical mechanics. I will write a partition function. I will write the propagator from there. No, now nothing. Now I'm writing a generic some Hamiltonian H naught, abstract Hamiltonian H naught, some abstract phi. Yeah, you wait. It will come. It will come. I'm doing the preliminaries now. So please wait for another 10 slides. It will come. Don't worry. So this preliminary slides will not contain anything about the infrared problem because I want to first set up what is.
Is there an infrared problem in the dark matter scattering? You wrote a scattering.
The infrared problem for any thermal field theory will always be much more acute. Instead of log divergences, you will get linear and sub-divergent log divergences. So the problem in the thermal field theory is to show the cancellation of the linear divergences and the log divergences, and that comes because of your distribution function, the Bose distribution function, which in the soft K limit looks as 1 by K.
So dark matter usually has mass, right? So I mean, why would there be an infrared?
Just wait, no patience. Yeah, it will come. I promise you, it will come. Okay.
But the first line was just one should not look at it. That's what
Maybe I'm sorry. Maybe I should not have put it. Yes. Just erase it from your mind. Okay. No, you are right. Actually, I realized that too. It's a problem of trying to take an earlier talk and then simplifying it in a way that is not probably the right thing to do, because now we have gone somewhere else, right? This is a generic Hamiltonian, generic phi. I hope nobody is confused. I'm very sorry. Full apologies. So here I was, just to remind you, we had written psi in terms of the complete set of states phi n, and I want to really calculate an, because an gives you the probability amplitude for this transition. This is exactly what you have done in your, I think maybe even BSc nowadays, certainly in your MSc. So here I write I d psi by dt is h, which is h naught plus v. Now, so I have now to differentiate psi. It has two terms which are functions of t. So one will give you an dot, one will give you en. And then if you rewrite this thing, you can see that en on un is like h naught on un. And therefore, this whole thing is just h naught psi. So this h naught and this h naught will cancel. So you get v psi is related to an dot. Now I want to get a specific solution for an dot, not as a sum. So to remove the summation, I multiply by a um star, integrate, and use this fact that they're orthonormal states, and therefore I end up with this. So the am dot, sorry, the i's are, this is I times am dot d by dt of a is related to the matrix element of the transition of n going to m under the action of this potential V. Okay, this is the standard thing to do. Now, if the interaction is weak, we can, I did something, sorry. If the interaction is weak, of course, I can just assume that it goes into one of the states A beta, and the probability of transition to others is small, so that I pull this out of the equation, and I can really write this equation like this. So some alpha goes to beta, and all the others are suppressed, and there's a whole argument which leads you to the Fermi golden rule with density of states and stuff, which I'm not going to go there. So this is the initial setup about how the transition amplitude is written. And if I want to go from alpha to beta, this is called A of beta. And the integration now is from 0 to t, and this t essentially will now go to, capital T will essentially go to infinity, right? So now I rewrite, therefore, this transition amplitude from an initial state to a final state is given as this AF, whatever I wrote over here, A beta, the final state is now F. At some average temperature T by 2, I could have done from minus T to plus T, then I would have got at 0, which is where the potential is turned on, and then I take T to infinity. And what I have done here is that I want to write it in some 4-vector notation. So this matrix element is d cubed x and times dt. And so I've written this as d4x, pi f star v phi I. And you can write this whole thing in quantum field theory, and you will get a very similar relationship for the transition matrix element from an initial state I to a final state F. So I have shown you the non-relativistic calculation, and I assure you that if you do the whole thing properly in field theory, you will get exactly the same description. And this potential is described depending on what is the Lagrangian that you have used and the specifics of the particles at their interactions and whatever quantum numbers they have, right? So this is the starting point for me. So this is the transition amplitude. So of course, the square of the transition amplitude will give you the probability, and the transition rate is the probability per unit 4 volume, which is per unit volume per unit time. And the cross section, which is what is the quantity that I am interested in calculating, the cross section for a process I going to F. Those who were there yesterday, I gave you the example of electron muon going to electron muon. So the initial state is electron muon state, final state is electron muon state. So I and F are those initial and final states, is normalized WFI, normalized to the initial flux, because instead of having one particle, one electron on one muon, you will have a beam of electrons and muons. So, and then it can go into many final states depending on what the phase space allows. And all these normalized transition rates is finally called the cross section, which is a Lorentz invariant with dimension L square. So this is now my little bit of recap about what a cross section means. So this is what I'm interested in calculating, and what it needs for calculation are these transition amplitudes. And yesterday I talked about how it can be written in terms of these Feynman diagrams to which certain quantities can be assigned. Okay. Now I go to quantum statistical mechanics. So where do I start? I just do a little recap. You remember that this is the time evolution operator. So Hamiltonian, H hat is the Hamiltonian. If I want to go to a state Q, if I want to go to a state Q prime from a state Q, it goes under the action of this evolution operator. And what I am interested in, and you will see in a moment why I'm interested in that, is I want to formulate this in imaginary time. So I send t to minus I tau, t prime to minus I tau prime, where tau and tau prime are completely imaginary. So now I'm asking what is the amplitude for a particle. Sorry, this should have been Q, cut and paste problem. So from Q at tau to a Q prime at tau prime, that is given by this quantity. And now if you have learned your time slicing and your Feynman path integral formulation, you can go through the steps and you can work out that this can be written in terms of this action. This is because I have rotated it from time, real time to imaginary time. Instead of giving you the Lagrangian, it gives you the Euclidean Lagrangian, but don't worry about it, okay? So it's this, and so this whole thing is the action, and integrated over these this full path from tau to tau prime, with the boundary conditions that at tau the state is in Q and at tau prime the state is Q prime. Okay. Now you see that if I now I've gone to quantum statistical mechanics, and you know that you start with a partition function, and in partition function for a state at temperature beta, beta is 1 by t, can be written as trace e to the minus beta h. That is the standard definition. Normally you would write that as sum over states e to the minus beta en, right, where the en are the eigenvalues of that Hamiltonian. But instead I choose to write it in this fashion. I write the trace in the basis where Q are the operators which correspond to the position. So I can expand in any basis that I want. And now if you look at equation 1 and equation 2, you can see that they are looking very similar, which is why I actually did this rotation from IT to tau. And you can see that this is actually, the trace actually takes you from Q to Q. So the initial and final states are the same. So I can reinterpret the partition function in terms of this probability amplitude F to go from Q to Q, but from a path which goes from 0 in imaginary time to beta in imaginary time, or in real time, so from 0 to minus I beta. Okay, this is what I have done, and this is, I have written it again. You can see that this is the analog of this. Instead of writing the integral, I have written the integral LDT as the action. Okay, and this is the boundary condition, because Q of beta must be Q of 0, because I have a trace condition, so the initial and final state are the same. So this is important for us. Remember that the initial and final states are the same, so I have to identify the state of Q of 0 with the state Q of beta. Now I have got two backgrounds. I have understood what is there in scattering theory. I have understood what is there in quantum statistical mechanics, and now I can now go to asking how do I now, I'm moving towards the field theory and how to write the Feynman rules in the field theory. So now I have something which has a temperature beta, and now I write for now at this point, for those who have not seen this before, the functional approach to quantum field theory, you just look at it by analogy with the quantum statistical mechanics. What I have is I have written z of beta here, the partition function. Now I have generalized to z of beta comma j, where j is a current. I have just added a j dot q term over here. This is the old z of beta, and I have just added a j of q over here. And you can see that if I keep differentiating z with respect to q, with respect to j of tau, j of tau 2, j of tau 3, I will keep bringing down a q1, a q2, a q3, and so on. So if you remember that in statistical mechanics, a thermal average is defined as, say, for of n states as q1, q2 times e to the minus s beta divided by trace of e to the minus s beta, right? So you have operator expectation value at a temperature T is trace operator e to the minus beta h divided by trace e to the minus beta h, right? So that's what I'm writing over here. So this is my z beta, if you divide out, is the same integral without the q's, right? But this actually, you can see this right hand side is therefore the thermal average of these two operators, q at tau 1 and q at tau 2, and that is simply this, as what I said, trace of operator times e to the minus beta h by trace of e to the minus beta h. So I have now made this analogy with a 2-point function. So this is a 2-point function. It's a time ordered product of two functions with an expectation value over some temperature beta. Okay, and I have made a connection to the way in which this z of beta or its derivatives are written. Okay, now I have got this whole structure where tau is completely imaginary time. But in the first part of my talk, I talked about scattering cross section, where I went from t minus infinity to t plus infinity completely in real time. So it is not sufficient for me to just have T completely converted into an imaginary part which codes for the temperature, but I must also have a real axis for the T. Only then I can come back to doing scattering theory at finite temperature. So what are my requirements? I need an imaginary temperature imaginary time which codes for the temperature. IT become minus IT becoming beta, and I also need a real time axis to do my scattering theory. So now I therefore generalize this whole structure that I have, and this is called the real-time formulation of thermal field theory. So now what I do is, I had just talked about these operators q hat 1, q hat 2, etc. Now I say that let us look at a theory of scalar fields. So I'm just going to do everything by analogy. You have to do some rewinding and restarting, but it will essentially come to the same thing. I now have a field theory of scalar fields, and I'm going to write a similar kind of thing, just as I wrote time order of q hat 1, q hat 2, q hat 3. I can write a time ordering of phi hat 1, phi hat 2, phi and n point function. So this will give me a green, it's called a green function, which is an n point green function. And C, even though this is a connected green function, the C doesn't stand for connected, but it stands for the path or the contour which I will actually describe. Okay, So this time ordering becomes very important, because now this path that I have to take in the field theory is a complex time path. Why is it complex? The real axis is required to do scattering theory, and the imaginary axis is required to include my temperature. So my path becomes a little complicated or complex, but it is actually complex. And so I can actually label it with a parameter V. So T is Z of V, and V is, I will arrange it to be monotonically increasing, real, etc. And then everything goes through. So if I go back to my 2-point function, phi hat of x, phi hat of x prime, there are two terms as usual. With the first, the time ordering is T is less than T prime. That is indicated by theta of t minus t prime. And the second part is when t prime is greater than t, that is indicated by theta of t prime minus t. And you can again construct a partition function in terms of these fields. You can obtain these 2-point functions, or in general they're called Green's functions. The 2-point functions will give you the propagators, and I can write a partition function which looks like this. Okay, it doesn't matter what the details are. Okay. So now this path, as I said, has to go through all the arguments, and this is my path. So this is a typical path that is chosen in thermal field theory. So this is the real axis. So you can think of Ti actually mapping to minus infinity, this mapping to plus infinity. So the path will take you from along C1, then to C3, and somewhere in between. So this is the imaginary time axis 0, real time axis 0, and this is the imaginary time axis minus I beta. So I go along the real axis, then I come down to some I sigma, sigma is arbitrary, and then I go back to minus infinity, and then I come back to minus I beta, because we know that the integral goes from 0 to beta, right? And this sigma is actually arbitrary. There are many solutions for sigma. You can take them to be whatever you want. I take sigma to be beta by 2. So I have drawn a very symmetric contour that this length and this length are the same. Okay. So what have we now obtained? We have obtained a path which includes the real axis, which is required for scattering. And then I have included a path where the imaginary time integral goes from 0 to beta. So when I start from here at the imaginary time equal to 0 and end up here at imaginary time beta, then I can include my thermal field theory. But you can see that now I have fields which will live on both these. These I can make as small as I please, I don't care. But these are the really long lines going from minus infinity to infinity. So you see I have two types of fields. Fields which live on C1 are called type 1 fields. Fields which live on C2 are called type 2 fields. A little bit technicality, because you're going from plus infinity to minus infinity. You have to make your theta function correct and well defined, but all that can be done. So you can make sure that t is non-increasing and define it correctly. Whatever it may be, you have two types of fields. So what has happened is that by writing a thermal field theory in real-time formulation, you have now doubled your fields, so that you have type 1 fields. So you can have a propagator for type 1 fields. You can have a propagator for type 2 fields, and you can have propagators which take type 1 to type 2 and type 2 to type 1. Okay, so you have done a field doubling. Then the real axis contains the real field. So the physical fields are all of type 1. You can think of the type 2 fields as kind of ghost fields. Okay, and the other thing is that because of your trace term, you have trace of e to the minus beta h, you have to identify the field at this point with the field at this point. And this gives you periodic boundary condition phi t naught is phi t naught minus I beta for boson fields, and minus because of the fermionic field is a minus sign. And the propagators also will have the same condition, and this is called the KMS condition. Okay, so here I have now propagators. So there are two kinds of propagators. Doesn't matter what they are. I will not worry about these. I will actually explicitly show you what these propagators are in the next slide. But just remember that there are now two types of fields. So in some sense, what you can say is that the real axis captures the quantum fluctuations. That is the only thing that is there at 0 temperature. And this one captures the thermal fluctuations. So what does the thermal fluctuation say? It says that now you have a quantum field theoretical system at some finite temperature. And vacuum, of course, I'm not sure if you have learned about this. Vacuum in field theory is not nothingness. It has infinite number of particles which have net 0 charge of everything. But now these particles which are there in this thermal field theory are distributed according to some distribution functions. For example, you have say n number of bosons which are distributed according to the Bose distribution function, and you have some other n prime number of fermions which are distributed according to Fermi distribution functions. So that also appears in your, so that means whatever is running and whatever thermal fluctuations you have must respect the quantum statistics of the problem. Okay, so with respect to that, the propagators are written. So I'm just writing down the Feynman rules now. At this point, I think I'm going to lose some of the younger audience. I'm sorry, but we have talked about the propagator. It takes you from point A to point B. If you look at this now, you can see that the propagators are 2 by 2, right? So the type 1 and type 2, and then there are off diagonal elements which take you from 1 to 2 and 2 to 1. Now you can see that the propagators are sum of two parts. The first part is t equal to 0, t independent part, and the second part with the, this is the distribution function, I'll talk about it in the next slide, and the explicit dependence on beta here is the temperature dependent part. So it always comes for all, whether it is scalar or photon or fermion or whatever it is, it will come as a sum of two parts. And you can see that this propagator, this 1 propagator, is the usual scalar propagator, I by p squared minus m squared. For photon propagator, it will be minus I g mu nu by k squared, because there is no mass, so it is the mass 0 part of this propagator. And this delta star comes because in C2 you're going backwards in time, and that gives you the delta star term. And you can see that because these are thermal fluctuations, they are all on shell. This is what I talked to some of the students about yesterday. They satisfy the mass shell condition. They are actually real particles, because the heat bath actually contains nb number of real bosons, right? So this, it is distributed according to nb, and it is sitting on mass shell. So you can similarly write propagators for the fermion, propagators for the photon, and here the plus sign and minus sign come from the symmetry and antisymmetry of fermions. And for the fermion propagator, you can see that just like you have at 0 temperature, all the 0 temperature, finite temperature, all the parts give you the same numerator p slash plus m that was there at 0 temperature. Okay, so these are the Feynman rules. And then the vertices. So if you remember, the vertex for photon interacting with fermion is minus IE gamma mu. If it is interacting with a type 2 fermion, it will have a extra minus sign. Similarly, for the scalar, for a type 2 fermion, it will have an extra minus sign. So all the ghost terms come with an extra minus sign in the vertex. So this is the, and so this is the photon fermion interaction, photon scalar interaction, and photon scalar can have two interactions. The one which looks like the fermion interaction, and one which is called the seagull diagram. You have to kind of extend your imagination to see the seagull over there. Okay. Now I come to the fact about this operators here, the Bose distribution function and the Fermi distribution function sitting over here. So let's get rid of this NF first. The Fermi distribution function is e to the beta E plus 1. So when E is small, P naught is small, it goes to a constant which is half. But the Bose distribution function goes to 1 by k naught because of the minus 1 factor. So you can see that there is an extra 1 by k naught in the soft limit when k goes to 0 because of the NB. So I have just written to remind you, excuse me, typically the photon propagator has a I by k squared and either plus or minus 2 pi delta k squared times NB times some matrix element which I don't care about. So you can see that here this structure looks like 1 by k squared. And this structure delta k squared also has the same dimension of 1 by k squared, but this NB adds another 1 by k naught, which means that this has 1 power of k more in the denominator than the t equal to 0, 1. Okay. So when we do the cross-section calculation, you will find that this will have logarithmic infrared divergence and this will have linear infrared divergence, which means it will also have a logarithmic subdivergence. And if you want to have a well-defined infrared finite theory, you must cancel both of these. And so I will tell you what it means to have infrared divergences and how you can cancel them. Okay. So, good. So I don't want to start with this. Let me do one thing. Okay, fine. You can stare at this. It doesn't matter what it is. I will actually write down on the board. So I will show you one example and then I will go to the result, because I think the rest of it is very detailed and may not be interesting. So I will just write down the thing. So what do you mean by an infrared divergence? Let us take a very simple example of a scattering problem. So the simplest scattering problem I can look at, thank you. So I say that some fermion P, momentum P, goes to a fermion P prime, and this is some photon. Let us say it has momentum K, and let's call this vertex V. I don't care what it is. It doesn't need to be a photon. It can be anything, bringing in energy into the system. And technically, that has to be a hard momentum. It cannot. Well, let's call it Q. Then let's not call it K. Let's call it Q. It has to be a hard momentum. So usually K is, we'll talk of a soft momentum. So I can compute this cross section. So those who know what it is, I can compute the matrix element will be U bar of P prime. I have a minus IE. I don't care about the minus. I just have some vertex factor and then U of P, right? Now let me ask what happens when I do a correction to this. Let us take, I will take a photon correcting this, okay? And let us say that therefore, this has a momentum P prime plus K, which then flows this way, which then flows this way. And you can see that K can be anything from 0 to infinity. So if I want to write this matrix element, so let me call this M1 matrix element, this will have an integral over K, the same U bar of P prime, let me write U bar P prime for short. Then I have to write a minus IE gamma mu at this vertex. I'm not going to write the gamma mu's. I have to write a propagator at this vertex. Then I will have to write gamma V vertex, which I don't care about. And then I don't really need the rest, but let me write. Okay. And now you just count the leading order here is there's a P prime here, there's a P here, numerator has no K. So this looks like D4K. Now P prime squared is M squared. So the leading order here is 2P prime dot K plus K squared. And this will contain 2P dot K plus K squared. And then of course I have the propagator for the photon is minus I G mu nu by K squared. So I have K squared. So you can see that I have K squared, and D4K by K to the power of 4 has both ultraviolet and infrared divergences. It diverges both because this integral is from 0 to infinity. It will diverge both in the ultraviolet when K goes to infinity, in the infrared when K goes to 0. So what Grammar and Eni have shown is that suppose I replace this G mu nu this propagator G mu nu that you see over here for the photon, I can do a subtraction like this. I write it as G mu nu minus B K mu K nu plus B K mu K nu. And I'll define B later. This is called the G photon part. This is called the K photon part. And they showed that all the infrared divergences are collected inside K and that G photon is finite. And what I will show later, what we have done in our proof, is to generalize the B that they have used to the thermal case and then show the infrared divergence cancellation that way. So I will just show the infrared divergence cancellation for this one term. So what do I have to do now? I have to now write this term, and I don't care about, okay, so I will write M1 of K, which means that I replace G mu nu by B K mu K nu. And I'm only going to look at this portion. So just to make it life easier for me, I have a D4K U bar P prime. Now gamma mu is multiplied by B K mu K nu. So gamma mu K mu will give me a K slash here with a B outside and a P prime slash plus K slash plus M dot dot dot. I don't care. And the denominator is this. Now if I move this through, I get 2P prime dot K minus P prime slash K slash minus M K slash. Now what happens? P prime acting on U prime is M, so this becomes M minus M, which is 0. So first thing to notice is that it comes out as the difference of two terms. In this particular case, one of the terms cancels, you're left with P prime dot K. And you notice that I can write P prime dot K as P prime plus K squared minus M squared minus, this is a very standard trick, by the way, in field theory. And now I bring back this denominator. right? And this is 0 because p square is on shell. So, and this is 1. So you can see that all the k dependence, and this will happen the same way for this side. This will now act on UP and give you the same result. So you can see that what will be left is that you will get B times the lower order matrix element, which in this case is M0. So there are just two things that you have to notice. When I insert gamma mu, k mu, dot, 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 gamma nu, k nu times B, this is the insertion for the k photon. I will get, this B will be left over and it will be proportional. So M1 will be proportional to M0. You will find that M2 will be proportional to M1. And so each one will be proportional to the lower order matrix element, which will not contain that particular inserted K. And in particular, because here these terms went to 0 because I had a U bar P, but if I have a nth order graph with n photons, then you just get a difference of two terms. So these are the two key points to notice. And with that, you will see that this B I will define, and the way B is defined, because 1 by k squared is still left actually, and you will find that B has a 1 by k squared definition, and there's already a 1 by k squared. So this will capture the entire infrared divergence. And then you have to have a proof that the remaining part, this G mu nu part, is infrared finite. Okay? So this is the core of the thing. The rest of it, if you don't understand, doesn't matter. It's all just details. You can switch off the light now, I think. Yeah. So this is what I'm saying. So this is the, now I am going to finite temperature. I will start with the theory of fermions. For fermions, I have a construction of B. Now what I have done is that instead of taking one photon, I have taken 1, 2, 3 up to R vertices here, 1, 2, 3 up to S vertices here, and N is R plus S, so I have an nth order graph. So some of these insertions can be real photons, some can be virtual photons, it can be anything. Into this graph, I want to insert the N plus 1th photon. So there will be 2 more vertices, and then I will take the k photon part, and these are all the diagrams, it doesn't matter. All I want to highlight is that now there is much more notation because I have a thermal field theory. It has indices type 1, type 2. The propagators are complicated, they are matrix valued. So forget all the indices. What I showed you there was that there's a difference of 2 terms. What I'm showing you here is that, let me consider this line, which has S indices, and I have to insert a photon anywhere, my n plus 1th photon. I can insert it to the right of 1, I can insert it to the right of 2, right of 3, right of 4, right of S, up to left of S plus 1. So there are S plus 1 graphs. And any arbitrary one, which is, say, at some Q to the right of Q, I can simplify this K slash term as a difference of 2 terms, which I label as MQ minus MQ minus 1. Now, when I add all the terms, they will cancel in pairs. So the first graph shall be left out. I'll tell you why. But the second graph onwards will give you M2 minus M1 plus M3 minus M2. So M2, M2 cancels, M3, M3 will cancel. Everything cancels in pairs to give you this. And the first graph gives you plus M1. So M1, M1 cancels. You'll be left with only the insertion, which is sitting here, just to the right of this vertex capital V. Okay? So once all the terms cancel, and this term you can see will have no dependence on the K apart from that overall factor B. So this is the generalization of the proof. As I said, just too many indices are there, I cannot explain them all. But the key is that these subtractions happen in pairs, and the fact that these insertions give you always 2 terms which are A minus B term. Now I can do the same thing for scalar fields. Since scalar fields now have both 3-point and 4-point vertices, they are very painful, and many pages of proof, and we could not simplify it. You have to define something called a circled vertex and then do something, and you keep on doing it and then you get the same answer. So even if you insert photons on scalar fields, you will see this term by term cancellation, and the n plus 1th order graph will be proportional to the nth order graph with this coefficient B, which contains the K dependence and nothing else. So now we have done this for scalars, we have done this for fermions. Now we are ready to look at, finally, sir, dark matter has come. So now that I have put the fields together, I have a Lagrangian which contains a dark matter particle which interacts with fermions, charged fermions and charged scalars with certain properties, quantum numbers which I don't care about. All I want to say is that I can now use those old results in my new calculation. When I use those old results in my new calculation, what I have to do is I have to be able to write a graph which looks like having some initial p leg and a final p prime leg, because that definition of B, which is a little complicated, I didn't want to show you, requires you to define an initial line and a final line. So what I do is that I twist this graph around. So you can see I've written the same graph here. So this entire piece, one fermion and one scalar part is the p leg, and this final fermion is called the p prime leg. Now you see that I have a different vertex here because this is now the coupling to the dark matter particle. So I have three parts. So this is one part. So I can have different kinds of insertions. I can insert the virtual photon to have both vertices on this. I can have one vertex here and one vertex on this line. And on this line itself, it can either be on this half or on this half. Here is the scalar, here is the fermion. If the whole thing is on this leg, it can be both on this side, both on this side, one here, one there. You have to just work through all the possible algebra and do it. So the easiest part, of course, is when one is here and one is here, because then they kind of factor out. So that is what I have written here. So no, so actually what we showed is that independent of the interaction of the dark matter, so it's a generic Lagrangian, it will go through. The cancellation will go through actually. So you can take any Lagrangian. That's why I said I don't really care what the Lagrangian is, provided that, so okay, so maybe I should have gone back there. Now I should highlight the particular statement that I made. This is, I promised to tell. Now that I have said so much, okay. So at high temperature, you have the dark matter annihilating to FF bar or FF bar going to chi bar, and they stay in equilibrium. Okay. Now what happens is that when you are coming towards phase out, you believe that this. Let me show you the Lagrangian here. Sorry. Why do it? Okay. So when you look at this Lagrangian, I've just taken portion of the Lagrangian which is of interest to us, but this dark matter has this interaction with both the scalars and the fermions. We have assumed TeV scale dark matter. Actually, it's not required. Okay. So because it's heavy, the freeze out will occur after the electroweak phase transition, which means your W and Z are heavy. So the only thing that can give you an IR divergence is the interaction with photons, which is why we could reduce it to a theory of photons and electrodynamics. Okay. So now if you're saying that you have light dark matter and you're even before the phase transition, then everything is open and I have no idea what the answer is. Okay. Similarly for QCD, that the moment you have self interactions of the gluons, then even, as I said, even at NLO I could not find a factorization. So I cannot reorganize anything to see the factorization at all. Okay. So that is the short answer.
It's a very naive question.
Ask. Maybe I missed what you said.
But if it's interacting with photons, and is the dark matter supposed to not interact with photons?
Yes, so they don't. It's just that the corrections to these, the leading order corrections to the diagram. Let me show you. This is the diagram. This is the diagram. These are dark matter which are neutral, so they will not interact with the photons. The leading order corrections will come from the interactions of the F bar and phi.
So basically, the loop effects are basically
Yes,
photons.
they will be photons, W, Z, anything, blue, anything that you please. Now we are in a stage where we are saying that we are after the electroweak phase transition. W and Z are heavy, so there is no infrared divergence. I forgot to tell you that because of the presence of the distribution functions, there is no ultraviolet divergence in the thermal field theory, because NB will kill it at high momenta. Okay, both NB and NF will send your transition matrix to 0 at high momenta. So you have to only worry about the infrared problem, which is, as I said, more acute in the case of photons. The fermion case will always be infrared. They will not be infrared finite, but they will have the same infrared divergence as the 0 temperature part, which we know how to regulate. Okay. So now we are only worried about, yes, sir.
Model of eta practice, the dark matter is modeled with the eta prime with the dark matter. The calculation normally is done by coupling eta prime to electromagnetism by FHF. That's eta prime times FHF. FHF is a topological term which normally in QED one ignores.
Correct.
For an eta prime FHF, there's an interaction. So which is where there is some amount of eta prime, it rotates the spin polarization of the photon. So from what I know, some experiments have been attempted to detect the spin polarization in Italy, in Trieste, in the university, and also in the near Gransa, so there is a university, there is a experimental center. So,
But that is a pseudoscalar. Must be pseudoscalar then, right? Axion. It must be the axion. Yeah. That, I mean, you can. Yes, you can do axion coupling to FHF. But you have to just rewrite. See, that's the whole point. You have to just rewrite the Feynman rules, and then you have to include that in the interaction term. As far as I understand, that particular interaction is, see, what is giving you your divergence, right? The divergence is coming from your soft K terms, and your FHF is a topological term. I don't see where it is going to give you soft K terms. Huh.
is it not a eta prime is not zero, it's not a constant. So it's no longer a topological term.
Oh, okay. Then I have no answer to your question.
This is how they do the experiment.
I see. No, they have an axion coupling, but yeah. Yeah, it is a higher order term, of course, but that is effective field theory. Maybe I don't know. I mean, I don't know the answer. Whatever it is, I don't know the answer.
Your interaction is eta prime, FHF.
Yes, yeah.
That's what they
Huh.
use. We have also
That is that's what I thought it was topological, but it breaks it. He says, okay, so okay.
so this
Uh-huh.
spin polarization,
Mhm.
rotation through the medium.
I
So
see.
the eta prime medium with spin polarization of the photon rotates.
Mhm.
The amount of rotation you can measure.
Mhm. Yeah, but as I said, it will depend on the couplings in the theory. I mean, so I don't know the answer.
This is all I know.
Huh.
But I don't know whether it's how it influences,
I don't know. Narendra, you have any comment on this? No. Okay.
how it influences infrared temperatures, I don't know.
I have no idea. So I have to look at the coupling and tell you. Okay. I don't know what it is offhand. So
I don't think it was related to dark matter.
see, in a very technical sense.
I know eta prime is not dark.
No, but I mean, coming to that, even my theory is not really related to dark matter. It is a generic theory of, it is a generic thermal field theory of fermion scalars interacting with photons. Okay, so I am pushing dark matter because it's the hot, but otherwise it doesn't matter. As far as I am concerned, I don't care. Okay, so I agree with you. Yes, yeah. We have seen eta prime in the lab, and we know what it is. Yes, yeah, true. Yeah. No, but there are so many models. No, there's a U1 sector dark photon coupling. So how the dark photon acts. Yeah. So I don't know. There are so many theories of dark matter now. So I have not looked at all of them. I will go ahead. Yes. Thank you, TRG. So sorry, where was I? Yes. Please. Oh yes, in the numerator. Thank you. See, there is your answer. Yeah, because you have a divergence, right? It's F wedge F. So you have two D's. So that's a K squared in the numerator. You have no more infrared divergence. Yeah, you don't have. It's gone. I mean, there are K's in the numerator. Here, there are no K's in the numerator, right? Okay, fine. So I think, sorry, in the interest of time, and now it is getting more and more technical, I just want to make a few comments. Let me take a simple example, the simplest I could find, where I have, now I'm going to take this diagram, which has n vertices, and I'm going to ask, can I reduce it by adding an extra photon into something which is that same B object, which I have not defined, times the lower order matrix element, which does not contain any K. If I can do this, then I can factorize out my K dependence. Once I can factorize it, then I can resum it, and once I will exponentiate it, and then I can get rid of it, and then I know how to deal with the IR divergences. So that is the aim of this exercise. So let me say that now I have one photon on the P prime leg, one photon on this leg, which means either this leg we know how to deal with, it's okay. I have already shown you for the pure fermion case. But let's see what happens when I have an insertion either on this leg or on this leg. So there are two possibilities, right? So that's what I'm showing here. So either it was inserted on the scalar or it was inserted on the fermion. So what happens is that, I think there's just too many words here. I will show you in the diagram. So again, what happens if you take all the possible scalars? Yeah. It's a charge scalar. Yeah. Oh, well, I mean, you have to conserve electric charge. So the charge scalar. So I have so many terms. Again, I will get differences of two terms. And I will have one term left over, which is the insertion of the photon just above this vertex X. Now I will insert all possible ways the photon on the fermion line, and I will get two terms left over. So there will be cancellations pairwise. There will be one leftover term which is just outside 1, and there will be one leftover term which is just below X. And what happens is that the term below X and the term above x will cancel. So there is a double set of cancellation. Okay, and it is actually independent of the nature of this x. So there are some details which I don't want to go into, and you can do that. And then when both are on the same leg, I don't care. There is a lot of problems. So I'm here. I've borrowed the slide from Preetham, who was my student, who did this work with me. He's now a postdoc at TIFR. So what you get is this. You get a term which is proportional to the lower order matrix element. This is the only term you want. Then there are some 3 additional terms. This term turns out to cancel with the scalar diagram, which is the seagull term. This term cancels with the tadpole diagram, which is also the scalar contribution. And this term has no k dependence in the denominator. It is linear in k, and it is odd under the integral, and it vanishes. So all these terms cancel, and you are only left with an exact factorization with a t in the resummation, and therefore we are able to do all the things, and we can resum it. Huh? No, this is the nth order. N plus 1 is now Bmn. This is what I have done, right? I am doing all order case. That is why it is so complicated. So what have I got? I've got some phase space I don't care about. What is interesting is that this is my photon propagator apart from the g mu nu term, which I had taken out, right? And you can see that I have a delta function t mu comma t1 and t nu comma t1, and t1 are the external legs. And we have said in the beginning that all external legs must be type 1. This is very important for us for the cancellation, which means that I will get a d11 times something, I don't care, I call it j squared. And in fact, this you can show that this B is universal, just like in zero temperature. It doesn't depend on the spin. There is a Low theorem which says that. And here also the same thing happens. This I'm going to skip. Oh, okay, I just forget all the top part. Now you have to do you have to show that this is the K photon insertion. You have to show that the G photon insertions are finite. Extremely tedious. I don't think the referee even read that part, but I promise you that it works. You have to just do it term by term. Everything cancels, and it all goes through. So now you have to show that I have pulled out B times something. The capital B contains my K factor, which is soft and infrared divergent. I have to now see how it cancels away, because I cannot have a cross section which is divergent, right? So what I'm going to do is that I know that there are n photons in the final state. They're identical particles. So the cross section, the matrix element will be suppressed by 1 by n factorial times mn. And I can rewrite this in some term. It doesn't matter what it is. And once I rewrite this summation, I can pull out a B power n. So if I now add all the contributions, 1 photon correction, 2 photon corrections, up to infinite photon corrections, this B power n by n factorial will go as E power B. This is the usual Surukov resummation of soft photons. This therefore also happens in finite temperature field theory. You are left with some finite part. So if I square the matrix element, that is what gives me my cross section. You remember, square of the transition amplitude gave me cross section. When I square this, I'll get E power B plus B star. So now how do I get rid of the E power B plus B star? What I have to understand is that just I have inserted virtual photons in my cross section, I can also insert real photons in my cross section. And since there was no internet in the hotel yesterday, I could not find a graph. So I can write a graph which looks like this. And I can either emit a photon from here, or I can emit a photon from here. And those soft photons will also have divergences. And what happens is that when that photon is very soft, and you cannot really separate it out from this fermion, then it looks like a graph where P gamma goes to P prime. And therefore, this cancellation, very unlike ultraviolet divergences, happens between two different cross sections, not matrix elements. And this, therefore, you have to now, I'm not going to burden you with this. You can repeat the same thing. Here, the K photon will come from the polarization spin sum of the real photons. And then you can do various things. The key part to note is that in the case of real photons from a heat bath, you can have both emission and absorption. So your phase space, this is the usual, theta of K is the usual phase space for emission at zero temperature. At finite temperature, you have an extra term. This NB again gives you your infrared divergences. You can now crank the whole thing through. I am absolutely not going to do it. All I'm going to show is that your final cross section will depend on this quantity. E power B plus B star came from the virtual part. B tilde comes from the real part. I'm just writing it here. You can see that if I expand when K is small, leading term here is 1, leading here is 1. So 1 plus n cancels with 1 plus 2n, which is coming from the virtual term. And therefore, the infrared divergences will cancel again to all orders in the perturbation theory. Okay, fine. So I'm not going to say anything. The proof of infrared finiteness of G is very tedious. I'm not going to go over it. And I am not going to go over this because I think everyone is saturated. I will just say that we have now therefore computed explicitly the one next to leading order cross section for this annihilation process. So this is the diagram that I already showed you, and it has 1, 2, 3, 4, 5 virtual corrections, and it has 1, 2, 3 real corrections. And because if you have, we have Majorana chi, so you have the cross diagram. So you have to have all the 5 cross diagram corrections and all the 3 cross diagram corrections, and there are some 100 diagrams, but you can do it all. So what I will just show you here, the results of that calculation. So first of all, explicitly we have shown it to all orders explicitly at NLO. We have shown the cancellation of the soft divergences in this theory using the same technique. However, we found to our shock and horror that the grammar in any technique does not isolate the collinear divergences. But we also showed that the collinear divergences cancel in between the real and virtual diagrams, but it's extremely subtle and not at all like the zero temperature case. So we are still writing the student is still writing the paper. I hope that he will finish soon. And it is a very interesting result that we have got. And I've looked in the literature, but I'm not able to see any analog of this earlier. There were some statements, similar calculation done by Beneke and friends some time ago, but they have not made any mention of it either. So, but they are very interesting results in the collinear case. See, for them, see, collinear divergences in QCD, even infrared soft, you can stuff it all into the Parton distribution functions. Here I have QED, I have to have exact cancellation. I mean, this is the Bloch-Nautz theorem, which is the analog is the KLM theorem in QCD. It's true. You expect it to happen. So at finite temperature, this is the first time it is shown. But it is true that it will happen, but they never bother about it. They just stuff it into the either distribution function or fragmentation function, and they are done with it. Yeah, but that's what I said. You can absorb these in the definition of the Parton distribution functions. It doesn't matter. You don't have to show they cancel because you know that you don't care about it. It's an unknown which you absorb in the distribution functions, right? So it doesn't happen here. So the final 2 remarks I think is so now we have computed both the virtual and the real corrections. Both are proportional to t squared. Unfortunately, it turns out that, okay, I didn't make the statement, I should have made it earlier. The leading chi goes to FF bar is actually helicity suppressed in this model. It turns out that even the NLO virtual contribution is helicity suppressed. We were hoping that will be lifted, but it turns out, it looks like because it's a 2 going to 2 planar process, helicity suppression is not lifted. So this is some correction term. However, when you have real corrections, now you have 3 particles in the final state. There is no more helicity suppression. And in fact, here there was an extra scalar mass squared suppression that has been removed in the real case. So this is the paper that we are writing up. So it looks like the real corrections can be actually significant. Now at some point you have to put this into some Boltzmann equation and compute the relic matter densities, and hopefully we will do that next. But right now we have just computed the cross sections. So this is work done so Prabhat is currently a student here. Preetham was a student as a postdoc at TIFR. Debojyoti is in Delhi University. And this work was started very long ago. And for years I struggled with the QCD, and I have given up now actually. I think now permanently given up. So I'm just happy that because of dark matter we could re-look at these things. And thank you very much. I think it is there. Yeah. Okay. No. No, here also they don't give any IR divergence. Proof is complicated because you see the G photon, see what happens, the scalars ruin everything. The fermions factor very nicely because of this. No, but whether you have NB or NF, okay, anytime you insert a fermion, it's finite. That we could prove. That part will also go into the G photon. I mean the G contribution. But what happens is that when you have a G photon, you have possible insertions. I think I have shown it here. Yeah, for the scalar field also it's hard. So we have a separate paper on the scalar field, which is also showing very complicated. I think nobody had done it for the scalar field. We had only looked at fermions, right? At that time. Where is it? Sorry, where did it take a look at scalar? Scalar, sorry. Okay, so what happens is this: you have two possibilities, because in a scalar field, I can insert the new photon here, which is what the fermion does, but I can also insert the photon at an already existing vertex. Now, this makes life very complicated. So, what we define is something called a circled vertex. An insertion to the right of one plus an insertion at one together is called a circled. I think, just in case somebody asked, I have written it in the backup slides. So what happens is, if I have a insertion between q and q minus 1 and an insertion at q, you can add these two together to form a circled vertex called mu q, and then you will have some very complicated identities which have some kind of a partial cancellation, and the remaining cancellation you have to deal with explicitly, as it becomes very dirty, but it goes through. But that called, and even at zero temperature, by the way, that complication is there. So yes. Yes, sir.
First about remark, you said Boltzmann equations.
Hmm.
How does it come here?
No. If you want to calculate relic densities, you have to put the corrected cross section. See, you have a cross section for chi goes to ff bar. That tells you the rate at which chi is going away to ff bar, or of course the reverse way, and that frees out, of course, one will overtake the other, and that will give you your relic density, right? Now what you have got is that you have some thermal corrections to this, which unfortunately are small here, but in Friesen they will not be small. That we can see, but we have not computed it yet. Okay, so now you have to put in this new cross section which is thermally corrected, and then see how much, because now the relic densities are being computed, measured very accurately, right, to decimal places. So the no, just calculation of this term. So now the question is that, if you what is the collision term? It is usually calculated. You take the temperature independent cross section and do a thermal averaging. So what is done is that the collision term is written as sigma v thermally averaged over beta. But this cross section itself is a zero temperature cross section. So now what we are saying is that we are taking a cross section which contains the thermal contributions, right, and then doing the thermal averaging of that. So now how much correction will it make? So the virtual corrections will be like negligible, I can tell you, because it is suppressed again, helicity suppressed. But it looks like the real photon corrections may be substantial. And if we do that, I don't know what we will get. We have not done it yet, and we are slow.
Boltzmann equations comes in there.
Yes.
Let me ask you two small questions. All this will be simplified, or should you use shear Kelly formulation?
See, okay, they're all equivalent descriptions. Okay, they are not, I don't think there will be any difference. Yeah, they will not make any difference. Okay.
The last question is, without introducing the distribution function,
Huh.
I mean, jet physics, like this, you see jet single quads or other quads. So I don't want to use fat factors to put them together. Has anyone thought about infrared divergences there? You see the infrared divergences.
See, I mean, there is a problem here which I didn't talk about. There's a technical problem. See, we talk about asymptotic states. I talked about t going to minus infinity, t going to plus infinity. Now, I am much happier with doing the QGP calculation, because these particles are coming from outside, and then they are not thermal. Okay, they're coming from outside, they're seeing a thermal bath, and then they're scattering off the thermal particles. But now, if you take early universe, your dark matter is already sitting inside your thermal bath. I don't know what asymptotic states you have. So if you want to do something like this Faddeev-Coolidge kind of state, so you have these rest electrons, for example, and then you can rewrite your S matrix becomes well defined. Everything, there is no infrared divergence anymore, because your states are now these new states, right? But what does it mean in the thermal field theory when you have a bath which is essentially the entire universe, right? So I am very uncomfortable with that idea. So we actually tried, with Preetham, we did a lot of work trying to write equivalent Faddeev-Coolidge states in the thermal field theory. Technically, it looks like it may go through, but physically, I don't know how to interpret it. What do you mean by, because it's true? I mean, because you have massless excitations, you have your cloud all the way to minus infinity, right? But still, you can rewrite your Faddeev-Coolidge states. They have some new interpretation. I don't understand, some BMS super selection. I don't know what it is called, but whatever it is, I am happy with Faddeev-Coolidge states. So there are some states where you can absorb all these infrared divergences, have a dressed electron, and then you can move the cloud from minus infinity to plus infinity. Everything goes through. In some sense, they're also interacting at minus infinity and plus infinity, and you redefine them there. So in that sense, it's not an insurmountable burden that your heat bath is also extending from minus infinity to plus infinity. But as I said, we have tried, and you have to do some Bogoliubov transformations, and then some thermal content comes. It works little bit, but we abandoned it because we are not sure physically whether what we were doing was meaningful or not. And I am not yet sure whether I have understood that. And it was unfortunate for Preetham, but I have not done it. I mean, yeah. I'm sure he has many comments on this. Huh. Huh. It is a? Huh, huh. No, but this is also going, see, you're going from again t minus infinity back to t minus infinity. That doesn't change. See, you see your contour, no? See, that is the whole point. I mean, these are all the same things. I mean, yeah. Yeah. Otherwise, you cannot see. How do you include the temperature, right? Sorry. Here. So you're going from minus infinity to minus infinity, right? Yeah. Huh. 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 Hmm. Hmm. No, so I don't know why, but it's a good question. I have to think about it. Yeah.
Can you just show us the diagrams that you had? I still haven't understood which one is dark matter, which one is not. The one where you had the loops also in that. Keep going.
You mean the actual NLO diagram?
Yeah, I think the one lit up after this.
Yeah. So these are the chi dark matter goes to FF bar, which are the fermions, standard model fermions, and this is a doublet charged SU2 doublet charged phi plus phi minus. These are doublets, and this is a singlet Majoran. Yes, it's some extra field. Some BSM thing. Yeah. If I dare say it, you can go to supersymmetry and find such a Lagrangian, but I don't want to go there. This is a minimal model. It's a generic model. Yeah. You can go to any and I don't care. No, seriously, yes, you're right. I mean, you can. Yeah.
Photon diagrams are which basically have the divergences, and that's what.
Correct. Yeah. So yeah. Correct. Yeah. So okay. Now that we have asked this question, so now you can see there is a propagator here and a propagator here, right? Now and then of course there are final states. So now the propagator here can become thermal. The propagator here can become thermal. The propagator here can become thermal, which we have dropped because we have assumed this is very massive. So the distribution function kills it because it's a scalar, right? So you have to add up all those contributions actually. And if you take the real case, then of course what happens is that this propagator cannot be thermal. You remember the thermal fluctuations were on shell. So I can't have 1, 2, 3 particles on shell. So this will not be thermal, but the final states will be thermal because then the phase space will get the thermal contributions. So this is how the cancellation happens. You can see that, for example, if what I get is m0 times m1 dagger. So let us do m0 times m1 dagger. So it will be this times the dagger of this. And so I have a contribution which, let us say that this photon becomes thermal, right? So the analogous diagram is when I multiply m1 real times m2 dagger, which gives me the same as this, but the cut will be here. You understand? And therefore you can see how that order by order, one real, one virtual, they will come with opposite sign and they will cancel. Okay. I mean, that happens even at zero temperature, and you can show that, but you just have to do a little more hard work, but it happens also at non-zero temperature. Yes, thank you. I have to now stop the talk because I have got the final accolade. Yeah? Huh?
These propagators can become thermal by putting the cut here.
No. The cuts are everywhere. So if you want to look at it in the cut language, I can look at the square of the diagrams. Then I can cut it here. I can cut it here, right? So if I cut it here, you can imagine the other half, right? If I cut it here, the photon is virtual. If I cut it here, then I have chi goes to FF bar gamma as the real thing. And you can see I put FF bar gamma as with a bracket somewhere, and maybe not here, because the gamma could have also been an incoming gamma, right? Because I can absorb it from the heat bath. In fact, if I don't have the absorption term, I don't have the cancellation. So it's extremely important that we recognize both emission and absorption from the heat bath. Actually, that is some work. I should have put that maybe. We did with Sorindu Gupta and Ravindran. I think it was 1995 or 1996. I should have added that paper. And that was, some Arthur Weldon had shown some generalization of Bloch-Nortzig theorem in kind of iconal approximation kind of thing to next to leading order, actually. So that understanding has been there for 30 years now, actually, that you have to do that. Yeah, I think, yeah. Thank you very much. Really.